Okay, so let's start today with gallium nitride, right? So let's now move from silicon carbide to gallium nitride, or we would also use mostly GaN throughout the lecture. So before I start, let's ask the first question: that why exactly GaN is faster? I think we have a lot of discussion in the past about why GaN is faster, right? So and what are the different system level problem does GaN solve? So technically in power electronics, we are always trying to reduce losses, volume, increase switching frequency and improve thermal utilization. So GaN is important because it improves all this dimension at device level. Its wide band gap, so WBG, support high electric field before breakdown. Its high electron saturation velocity supports very fast carrier transport, and its polarization physics gives us high density electron channel without conventional doping. This is why in the slide you see that I am emphasizing switching frequency, blocking voltage, efficiency and power density as the important factor for improving the performance of a power semiconductor. When you look at the figure 6.52, you could see that it do not interpret GaN as a replacement for silicon, but you should interpret it as an enabler for different converter design philosophy. For example, smaller magnetics, smaller capacitors, faster transient response, uh, potentially high power density at the end that would result in as well. So, but you should remember that these advantages are not just automatic. They appear when the gate driver, layout, packaging, thermal path, and EMI strategy are all built together in a very constrained, like coupled environment, I would say it, to get the best benefit out of this complete GaN power converter. Okay, so let's move forward with the evolution of the power semiconductor devices. Early power electronics was dominated by silicon devices such as thyristor, GTOs, bipolar transistor, BJTs, MOSFETs, and IGBTs that we have already learned throughout the lecture. I have been speaking a lot about what exactly silicon devices have been doing for over the past decade, and how exactly we move towards the wide bandgap devices. So it has to be understood that these devices were not replaced overnight, right? So it took a long period of time that one by one each of these devices were replaced. So each technology emerged because an application demand a new balance between the blocking voltage, or maybe a current carrying capability, controllability, and switching speed and cost were something that were derived upon. So thyristor usually served very high power but were very limited in control. MOSFET gave us fast voltage control switching, but their drift region resistance, uh, drift region resistance became challenging at high voltage. And IGBT reduced the high voltage conduction losses through conductivity modulation, but again, the stored charge slowed switching. I think this we have discussed a lot throughout the lecture. So silicon carbide and GaN entered when the system demand for both high frequency and high frequency came in place. So the three application layer that you see in this figure actually help you to understand the transition. So we started from infrastructure, right? So that would be somewhere in very high voltage class. Then we have the uh, home and industrial power system. So that would be a bit lower voltage class and power class as well. And then we have the personal low voltage systems like mobiles and other things around it. So the key historical message that could be conveyed out of this slide is that the power devices evolve whether the old material system reaches the practical compromise limit. Right? So this also was discussed in the past, that it's more about the material need that we want to have to make sure that we are able to achieve the right properties from a power converter or a power or system. Now let's summarize the material identity of the GaN. GaN belongs to the 3-nitrile family together with AIN and IN in, so that's aluminum nitride and indium nitride. This family is fundamentally different from silicon because it combines a wide band gap with strong polarization effect. The wide band gaps gives low intrinsic carrier concentration, and better higher temperature blocking. The higher critical field allows the device to block voltage over shorter distance, which directly helps to reduce the resistance and the capacitance. The high electron saturation velocity means that carriers can move under high electric field, which is really crucial when we want to switch at nanoseconds. The final point is that the GaN is a direct band gap material. It's, it's not the central for the power switching, but it explains why GaN becomes famous first in optoelectronics, especially in LEDs and laser diodes. For power devices, the most important message is that GaN is not just merely another semiconductor, but it has to be looked around as a material platform where high field strength, high speed, and I would say heterogeneous engineering, all these things comes together. So let's get introduced to the very first order trade-off, right? So suppose a carrier has to travel through a path length L. If the material can sustain a critical electric field, which we defined as EC throughout our lecture, then the maximum blocking voltage scales as VV equals to EC times L. So if we want a high voltage device, traditionally we increase the distance over which the voltage is supported. That means we increase L, right? But the increasing distance has a cost. The carrier transit time increases and the cutoff frequency decreases. The second equation that you see in here expresses this as a relation of Ft to the saturation velocity divided by the carrier length path. When we multiply breakdown voltage and Ft, the path lengths cancel out. This is a powerful observation because it tells us that a voltage frequency product is fundamentally material dependent. In silicon, this product is limited by lower critical field and lower saturation velocity. In GaN, both are favorable, but GaN gives us higher ceiling for devices that must block voltages and still switch very, very fast. This is the first principal argument. I would say rather than a data sheet, I think we will have a lot of data sheets added in our slides today. I will take you through one by one. So now let's move forward that we understood that there is some sort of like a limit, right? And this is what exactly we are going to discuss in this slide as well. So the limit is called as Johnson limit. VV when multiplied by Ft that we had in the previous slide is proportional to EC multiplied by P saturation. This is a compact way to judge high frequency, high voltage potential of a semiconductor. A high critical electric field allows a device to hold high voltage in shorter region. A high saturation velocity allows carrier to cross that region faster. GaN has got both things. This is why the slide says GaN is not only fast. If the material only had high speed but poor breakdown field, it would be useful for mostly RF application, that is in the gigahertz range, but it won't be useful in the power application. But if it had only high breakdown field but poor carrier transport, it would be good for blocking, but again not good for fast switching, which are something that we have been missing in the silicon devices. So GaN is combining these two properties together, and therefore it is very attractive for compact high frequency, high efficiency power converter. So for us, the design lesson from this slide would be that material figures of merit must always connect back to converter requirement. For example, breakdown voltage or voltage capability, frequency, loss, and most importantly, the thermal limits. Now, let's look at more detail into the 3-nitrile material system, right? So GaN, EIN, indium nitride can be combined to form ternary alloys, such as, like I think I discussed these things in the lecture, that usually this material are something which could be combined to form some sort of system. So for example, Al GaN, in GaN, right? So indium GaN, aluminum GaN, these are not just a minor material science detail, it is the basis for heterogeneous, or I would say not heterogeneous, rather heterostructure device engineering that we will be having it in the next few slides. By changing the alloy composition, what we are doing is that we are basically tuning the band gap, lattice constant, strain, polarization charge, and interface properties. For GAN HEMTs, the most important heterostructure is AL GAN or simply just GAN. The AL GAN barrier and the GAN channel create polarization discontinuity at the interface, which leads to the formation of, for example, high density two-dimensional electron gas. So it is called as HD2BEG. This is what exactly we define as. So in this you could see that how exactly the band gap and the lattice constant are actually varying across the nitride family. So from the designer perspective or designer viewpoint, this figure tells us that we can engineering electronic properties not only by doping as we were doing in the silicon case, if you remember, but also by choosing right material composition and strain. This is one of the defining differences between GAN devices and traditional silicon devices like the MOSFET and IGBTs that we have learned. So this slide introduces to you the crystal structure, right? So this is exactly the crystal structure of what exactly GAN looks like. I think I also introduced the crystal structure in the silicon carbide. So we mentioned that 4HSIC structure is something that is the most preferred one and most widely commercialized as well. So in this case also you have got the crystal polarity being defined for the GAN side, right? So GAN typically is a sort of like a wood side crystal structure which is hexagonal and lacks inversion symmetry across the C-axis that you can see. So there are two axes, A-axis, Z-axis that you see in there, right? So why this, depending on how exactly the crystal terminates, the surface can be either gallium phases or nitride phases. But why does this matter? Right, so this GAN phase or nitrile phase, why does this matter? Because in GAN, the direction of the polarization is tied to the crystal orientation. So gallium and nitrogen have different electronegativity, but the bonds are not electrically symmetric. In centrosymmetric crystal, internal dipoles would cancel perfectly, but in wood side, that is GAN, they do not cancel in the same way. So in this figure, you could see that you could visualize basically that the atomic arrangement has some sort of directionality. The directionality later determines whether the polarization charges appears in AlGaN or maybe just GAN stack, and whether electrons accumulates at the interface. For silicon devices, we usually know that the doping is critically important, but for GAN HEMT, we must understand that the polarity and the polarization is the primary thing, because the conducting channel itself can be created by the crystal and heterogeneous structure, or I would say created by the crystal and heterostructure physics that we have to understand. Now, there are two polarization mechanisms that we must distinguish carefully, and what those are: spontaneous polarization and the piezoelectric polarization. I think a few of you might have got some idea what could be this. So uh, spontaneous polarization exists even when there is external strain, because wood side GAN lacks inversion symmetry. The atoms are arranged such a way that the positive and negative charge centers but do not overlap. Piezoelectric polarization, on the other hand, appears when the crystal is strained. So in AlGaN or GAN heterostructures, the lattice constant are different. So the AlGaN barrier is strained when they are growing in the GAN. So this is structure, or I would say this strain changes bond angle and generates additional polarization charge. You can see in this diagram, which is sort of like a mechanical picture, I would say, when the when there is a sort of like a tetrahedral bonding environment is distorted, a net polarization appears, and the total polarization is at the interface, and is the combination of spontaneous and the piezoelectric contribution. This is very important because the discontinuity in polarization create seed charge, and that seed charge attracts to forms the 2DEG, right? And so polarization is not just, I would say, a material property, rather it's actually directs the current path within the GAN HEM devices. This may be looking too technical to you guys in terms of the terminologies that has been introduced, completely different from what we were in the silicon and the silicon carbide, but I would say they're not too hard. You just have to in a way try to follow what exactly is being discussed in the class. But yeah, GAN is completely a totally different structure, and we will have a few different new terminology. That's one of the reason you will also observe that in the um, introduction slide of in which I used to be very less amount of content in terms of, for example, after I introduced the basic electronics to you guys in the start of the lecture, I have been keeping the structure of the devices quite short, but in GAN we will have a greater discussion because it's a different structure and different property that we are completely discussing at the moment. So let's go on with the polarization induced 2-deck, which actually forms the current channel within the GAN devices. So this is one of the, I would say, most important slides in the part of the GAN. So you must understand this part. So at the ALGAN and GAN interface, the polarization discontinuity creates a fixed charge state. Nature must maintain charge neutrality, so free electrons accumulate near the interface. And these electrons forms two-dimensional electron gas or 2-deck. That's what we have been calling upon. It is called two-dimensional because the electrons are strongly confined in the vertical direction, but move freely in the lateral direction as well. So this gives us a high sheet carrier density and high mobility, which lead to low lateral channel resistance. For me, the teaching point is that this conducting path is not created in the same way that we were learning in the silicon, which was because of the inversal channel or the accumulation channel, right? So in a MOSFET, we apply gate voltage to induce inversal channel, but in GaN HEMT, the 2-deck may already exist because of the polarization and the heterostructure. So in this figure, if you look around, then you look into it, then you see that how exactly the polarization charge translate into in sort of like a carrier density or carrier density that we call in GaN. So when you understand the 2-deck, you understand why GaN HEMT are naturally fast and why they can be normally on unless specific measures are being taken. I believe you guys remember about the normally on and normally off devices, right? So normally on means by default the device is being on, and when you apply external biasing, then the device will turn off. But normally off means the device is generally off, and to turn it on you apply some sort of additional biasing from outside in device structure. Now let's go on with the normally on nature. I would actually say that GaN was originally started as a normally on device, and normally off devices was later being introduced. So now we try to understand or let's say we connect the 2-deck structure to a normally on problem. So a standard ALGAN or GaN HEMT contains a high density 2-deck at a zero bias state. This means that the source and the drain can be electrically connected even when the gate voltage is zero. So in device terminology, this is depletion mode. For RF amplifier, normally on operations are usually acceptable. So RF amplifiers are very low power scale, so they have a completely different mode of operation, I would say. So in that case, it's normally acceptable. But for power converter, it is a serious safety problem. You could imagine a half bridge connected to a DC bus. If the gate driver loses, or I would say, if the gate driver loses power and the device naturally remains conductive, then the shoot through or uncontrolled current can occur. The threshold voltage on this slide that you see here shows that the threshold completely depend on the Schottky barrier, the conduction band offset, and the seed charge density, and also I would say the thickness, ALGAN thickness, and the dielectric properties. So in other words, threshold voltage is not a gate driven issue, it is a heterostructure design issue, which is completely different than what we learned in the silicon devices. Now let's see how exactly we could achieve this normally off GaN devices, which is the preferred or practical solution for the power application. So the purpose is to shift the threshold voltage to a positive value, so that the device is off at, I would say, zero gate bias and turns off only when you intentionally apply some sort of positive biasing or positive voltage. One method could be that you increase the gate work function, making it harder for the channel to remain, I would say, populated as zero bias. Another is to reduce the 2-deck density by, for example, changing the AL content or barrier thickness. So recessing the basically the I would say recessing basically I would say basically recessing the algane barrier locally under the gate also reduces the polarization charge and depletes the channel. So PGAN or P-algane gates introduce, I would say, built-in field that depletes the 2-deck 2-deck at zero bias, and this is where exactly the interface charge engineering can shift the threshold. But every method has a sort of like a penalty. I would say, or we could also say that uh, there is always some sort of trade-off when we try to perform some modifications to get some benefit out of a particular material. So if we, for example, in this case, reduce the 2-deck density, then resistance may increase. So if we use PGAN, then gate reliability and the gate current limitations matter. If we resist the barrier, or each damage become very critical. So in this figure, you can therefore, I would say, in this figure, basically you could, I would say, interpret is as a design trade-off map and not rather loss like a list of solution that we are looking into. Now, uh, let's try to understand different planes. So there are different planes, I mean polar, non-polar and semi-polar GAN plane. So this crystal plane actually determines how strong the polarization effect is. So conventional plane in the GAN is polar, which means that it basically produces strong polarization field. This is because, or I would say, this is useful for generating high density 2-deck, but it can also create challenges when we want normally off operation or a stable threshold voltage. So non-polar GANs such as the A plane and M plane, this one, so this is where you see A plane and M plane, reduce polarization because the polar axis lies differently related to the surface, and semi-polar plane gives intermediate behavior with average polarization closer to zero. So in this figure that you see in here 6.60, you can see a geometric view in there. So it is important point that the most important point I would say is that the device behavior is not only determined by the material composition but also by the critical orientation or the by the crystal orientation. So in silicon power devices, crystal orientation matters for mobility and oxide interface quality. You remember that we were performing some sort of conductivity modulation, but in GAN it also directly affects polarization charge and channel formation. This opens a lot of like device design possibilities, but in a way it also complicates growth, I would say manufacturability, where it's difficult for you to perform wafer processing, and maybe also challenges in the uh, commercial reproducibility. So now we move towards an interesting GAN specific concept, that is the natural superjunction. If you guys remember, then we learned a bit about superjunction MOSFET in the silicon MOSFET, right? In the previous lectures, something similar is also existing, but it's called natural superjunction in gallium nitride. In conventional silicon superjunction devices, we basically used uh, P balanced P and N pillars. So the goal is basically to support high voltage when maintaining low on resistance. But in GAN, because polarization charge can naturally generate electrons and holes uh, at different I would say heterointerfaces, alternating nitride layers can behave like it is a charge balance structure. So under reverse bias, this stored charges can be depleted. When the charges gets depleted, the multilayer structure behaves like an insulator and it supports voltage. So this is where exactly in the equation you could see that the depletion voltage in terms of the stored charge sheet and the equivalent capacitance could be defined with how exactly they are related with the overall voltage that they can support. The important idea is that the polarization engineering can mimic charge balance principle of superjunctions without conventional doped PN columns. So in this figure 6.61, it gives you a helpful capacitor analogy actually. So initially charges are stored as interfaces, that's what it happens in the capacitor, but under bias the depletion removes the mobile carriers and the structure becomes blocking, right? So this is how exactly, this is a very I would say powerful example of how exactly GAN device design uses heterogeneous or heterostructure physics rather than only doping profiles. So this slide gives an experimental support for the natural superjunction concept. The fabricated devices that you see in here, this is in the scale of 100 micrometer. It shows breakdown voltage increases with electrode spacing. This is exactly what we expect if the voltage is supported by the distance over which the electric field is distributed. The key variables are critical electric field, anode-cathode spacing, and the depletion of the polarization-induced charges. In silicon superjunction, the performance depends strongly on precise charge balance between P and N columns. If doping is not balanced, the breakdown voltage and the on resistance are usually degraded. In GAN natural superjunctions, part of the charge balance arises from polarization-induced carriers at heterointerfaces that can reduce the need for extremely precise p-n pillar doping. So that's what you can see in figure 6.2, that the idea is not only theoretical, there are fabricated structures and measured breakdown trends. And the broader lesson is that I would say the GAN enables high voltage device architecture because polarization can be really used as a design resource. Now we understand about the on resistance and the breakdown voltage. I would say we are now basically returning to our familiar power device trade-off concept, which means that the on resistance versus the breakdown voltage. So generally they are a sort of like inversely proportional to each other, but a lot of things that has to be also considered while we say that they are inversely proportional. So in a lateral GAN fit, the total on resistance can be separated into R on, yeah, or I would say, I'm sorry. So basically, in a lateral GAN structure, the total on resistance can be separated into this RCH, that is the channel resistance, and the drift resistance. This is what you see in the equation that states that simply the channel turns basically depends on the gate length, gate width, and carrier mobility. So that's how exactly the equations comes in place. And the drift term depends on the drift length, which is related to the breakdown voltage through the breakdown through the BV divided by EC. So this equation. At low voltage, the channel resistance may dominate because the drift spacing can be short, and at high voltage, the drift region become longer, and the drift resistances become increasingly important. And that's what you see in the figure 6.63 there. For a designer, this means that no single GAN device geometrically that is optimal for all voltage classes. So low voltage, high frequency devices may be optimized around capacitance and channel resistance, whereas high voltage devices must manage electric field distribution and drift region resistance. The equation that you see in here gives a compact way to connect geometry, material properties, and I would also say that in a way converter losses at the end as well, because we are able to calculate the value of resistance from here. Now let's move forward and conclude in a way that what exactly is the design takeaway for power GAN devices. This slide could be like a sort of like a checkpoint for everyone. So we have seen that the GAN devices are not simply faster MOSFETs. Their behavior comes from three linked ideas. One is the wide bandgap material properties, the other is the polarization induced carrier generation, and the third is the heterostructure engineering. So the ALGAN or the GAN interface forms a high density 2-deck without intentional channel doping that gives high mobility and low resistance, but it naturally leads to normally on behavior unless the device is engineered otherwise, right? So GAN can operate at high frequency because high saturation velocity and low capacitance. It can support high voltage because of high critical electric field. But practical power converter design must manage gate drive, parasitic inductance, over voltage, EMI, thermal stress, and reliability. I would like you guys to remember this key message that GAN is a polarization engineered device. it is, if you treat it like a silicon MOSFET with lower capacitance, it will be a huge mistake, or I would say it would be a huge design mistake. So if you understand the 2DEG, or the field distribution, threshold control, and reverse conduction, technically you should be able to exploit the GAN very properly, and this is what exactly we are going to now go forward in the next slides. Before jumping into directly high voltage power conversion, I would say it's important that we learn a bit about low voltage power conversion as well, because I think in the I would say in general in the market, GAN is not reaching to higher voltage at the moment. It's mostly the lower voltage, I would say maximum 750 volt or 700 volt devices are there, and below that are something that is there, that is more widely being used. Okay, so low voltage does not mean that low importance, right? So you have to also think about high volume system, for example data centers, right? So data centers are quite widely being deployed in multiple locations worldwide. Everybody want to have data centers. So data center is, I would say, a high volume system, but it's operated at low voltage. Then we have the point of load converter, then you see USB chargers, then telecom supplies, and automotive auxiliary power converters as well. So these are all few of those that operates actually in few hundred volts. Few hundred volts means generally less than 200 volts most of the cases, or at max at 400 volts somewhere around. So in this system, the dominant challenge is often not blocking voltage, but reducing conduction and switching losses in a very small chip area. Silicon MOSFET have been optimized for decades, especially through trench and superjunction structure. However, you have to remember that silicon scaling has a bottom limit because its critical field is relatively low. GAN allows smaller drift dimension and lower capacitance at the same voltage rating. This is what exactly you can see in this tables. So in this table you can see that I'm comparing the scaling loss and eliminating the device dimension for SI, SiC and GAN. The important practical implication is that GAN can deliver high efficiency from much smaller die, especially when the switching frequency is really very high. Smaller die also means that a smaller capacitance, and further it reduces the switching losses. And at the same time, smaller die also means that you are able to insert multiple number of components in the same space that you were able to put up in a larger die system, for example with silicon or silicon carbide. But as always, you have to also remember that the smaller and faster devices demands much better packaging and layout design. Layout design and packaging are something that we have to learn. We will learn basically in the next semester. Now, let's try to understand the trend. So I would also say that we are speaking about scaling trends and scaling laws, but scaling is just a sort of like an intuition, right? So it's not like a universal law that we have to learn around. So I would not say it's universal, but you could take it as sort of like a empirical knowledgeable decision making situation that you can have with if you know these things. So technically, if you scale dimension as a factor of 1 over k, then several electrical quantities change together. I think this is also something that you could derive out of different formulas and equations that we have been working upon in the past, right? So blocking voltage reduces because the distance or the voltage support is reduced. Capacitance reduces roughly with area, and switching losses also reduces strongly. This is why device miniaturization is so powerful in low voltage high frequency converters. So smaller capacitance means we have to use, or I would say that we use less charge to perform turn on and turn off the devices, or I would say less charge must be removed during each switching cycle. And that's what the case is in the case of when we want to switch at megahertz frequencies. So at megahertz frequencies, this becomes critical because the gate drive loss and the capacitive loss repeats millions of times per second. Silicon MOSFET have been used aggressive scaling for many years, but wide bandgap devices extend the scaling window because they can support high electric field in a very short region. The table that you see in here could be interpreted or could be understood as if from the viewpoint of a converter frequency. At low frequency, conduction loss may dominate. At high frequency, capacitance and charge become equally important and even dominant. And therefore, a device with slightly higher resistance but much lower charge may outperform a low resistance device at high frequency. Right, so now we are learning about the trade-offs as well. Okay, so now we have to understand what are the different, like over time, what actually happened with the low voltage MOSFET structures, right? So this slide basically reminds us that low voltage devices progress as historically been driven by, I would say, cell density improvement. What exactly is this cell density improvement? So that technically I would say that you would be making different structures, so lateral, planar, and all those types, and then you would be maybe creating some trench and things around it, modifying the device structure to increase the cell density. So silicon MOSFET evolved from planar to trench gate structure and then to self-aligned trench structure. The aim was to basically reduce channel resistance and increase packaging density while still maintaining adequate breakdown voltage. This has been also discussed in the silicon and silicon carbide lectures when we were discussing about, right? So I showed to you how exactly different types of structures of the, or I would say arrangement of this P and NPN structure has been performed within different varieties of devices. The aim was in general to reduce the channel resistance and increase the packaging density, while we should be still be able to maintain the adequate breakdown voltage, because at the end we want to have higher breakdown voltage. This is what exactly is shown in this diagram that you see in here. So in a low voltage MOSFET, the drift region is not only a resistance component, channel and cell geometry also become very important. So GaN designers face a similar challenge actually. Although the physical channel is different, in GaN HEMT, we basically do not form a vertical silicon inversal channel. What we do is that we use lateral two-deck channel, right? So since the, I would say, the design objective is analogous, that means that we would like to minimize the resistance and increase the charge per unit carrying capability. That's why you also often, I would say, in general, you often see that GaN devices are advertised using figure of merit such as R1 times QG or R1 times output charge QoSS. I think we have learned a lot about figure of merit in the previous lecture. So the historical lesson is that device structures evolved towards reducing both resistance and stored charge, and not only the resistance alone. Now let's try to understand the DC and AC losses in the switching devices. So converter efficiency contains DC conduction losses and AC switching losses. So conduction losses decreases when the on resistance increases. Oh sorry, I'm sorry. So conduction losses decreases when the on resistance decreases. Right? In the simplified scaling that we have here, DC loss is basically proportional to R1 times the gate width. Increasing the gate width gives us a wider conduction path and low resistance, but the same larger device also has more gate charge, output charge, and capacitance. Therefore, AC loss increases with charge. The equation that you see in here, I would say this equation 6.10 shows the opposite trend in a way. So AC loss scales with QG divided by gate width in a simplified interpretation. The product R1 times QG becomes an important intrinsic device figure of merit. This is why a device with lowest R1 is not always the best device. In a 50 Hz rectifier, you may care mostly about conduction losses, but in a 2 MHz power converter, gate charge and output capacitance can actually really dominate. So for GaN, the promise is not low resistance, but I would say a favorable resistance charge trade-off. Then let's understand the different types of device structures. So as usual, in the previous, for example, there were lateral, planar, vertical. So in this case also there are lateral and vertical. So we will now, in a very brief, I would say, try to understand this too. So in a lateral device, you guys know that the current flows parallel to the wafer surface through the two-deck. This surface is excellent for high frequency operation because the channel is very conductive and the capacitances can be really small. However, As the voltage and current rating would increase, the lateral geometry would face some limitations. And this is where exactly the gate drain spacing must increase to support higher voltage, which basically increases resistance and chip area. So vertical devices conduct current through the bulk materials similar to the silicon carbide MOSFET and silicon IGBTs. Vertical conduction can offer high current density and better voltage scaling because the chip area and the drift thickness can also be used more effectively. This is what you see in this diagram as well. So this diagram basically compares the scaling of lateral and vertical structures, I would say. Most importantly, I would say that the most important takeaway is that it's not that the vertical GAN are already replaced has already basically replaced the lateral GAN. It has not actually, I would say. Commercial maturity is still much greater for lateral GAN HEMT, but for future high voltage and high current application, people are preferring to have vertical GAN structure. And there are a lot of research also going on in the vertical GAN structure at the moment. Now let's move forward to the gate charge and switching waveforms. So this slide basically is trying to link the device physics to the switching waveform. So during turn on, what actually will happen, and during turn off, what exactly could be possible thing. Let's start with the turn on. During turn on, what exactly would happen? The gate voltages generally rise, right? So this is what you can see in here, that there is a small rise in the gate voltage, then there is a stable point, and then again an increase in there. This is something that you could also relate with what we have learned in the silicon and silicon carbide devices. So if you remember, this straight path that you see in here is sort of like a Miller plateau, right? So what actually would be happening in this period of time? Generally, the gate capacitance would be the one that would be in general charging, or the device capacitances would be having some interplay in there, isn't it? Let's try to understand it a bit more. So during turn on, when the gate voltage rises, the drain current rises, and the drain to source voltage would basically fall. This timing is not arbitrary, right? So it's not like it happens in the way it wants to, rather it's determined how the gate drive charges the device capacitances. If you remember, there were three different types of capacitances, right? So gate to source, then gate to drain, and from drain to source. I won't repeat all those things, but I'm just speaking so that you guys could remember a bit about it. So during the Miller interval, that's this part that you see in here, a large part of the gate current goes into charging the a large part of the, I would say, gate current goes into changing the drain voltage rather than simply increasing the gate voltage. So what you see in this diagram is the measurement concept and the gate charge component. For GAN, the total charge is usually much smaller than the equivalent silicon devices, which allows faster switching, but low charge also means low noise margin. So a small injected current through a parasitic capacitance can disturb the gate voltage. So the same property that gives GAN a very high speed also makes it really sensitive to like surrounding things. For example, the layout, the gate driver impedance, and failure of symmetry in the design of the PCBs, and a lot of things, I would say. That's why I would say GAN requires very compact power and gate loops. If you guys remember, I spoke a lot about the power loop or the commutation loop, and also the gate driver loop, right? So this is what exactly was being said. Now let's understand the efficiency versus the switching frequency. These are some things that are really important to understand, that why exactly GAN is preferred, but also there are certain challenges. I would say this is where exactly in this slide we are trying to technically connect the figure of merit to actual converter efficiency. As the switching frequency increases, the AC switching loss would also increase. If two devices have same resistance but different gate charge and output charge, their high efficiencies can be very different. Sorry, their high frequency efficiencies can be very different. So the figure that you see in here shows that devices with low R on and QG, right? So low R on and QG, this is where exactly you see in there, right? So that is able to maintain higher frequency as frequency increases. This is the reason GAN is so attractive for compact DC-DC converters or different other topologies like resonant converter topology that we are going to learn in the next semester, operating in the megahertz range. But when I want to technically stress this statement in the block, then I would say that reducing only R1 is not sufficient. A large device may have low conduction loss but high capacitance, and at high frequency, that capacitance must be charged and discharged during every cycle. Therefore, an optimal device is not the largest device, it's the devices that balances basically the conduction and the switching losses for the actual operating point, or maybe the operating point under consideration. I think I also mentioned, yeah, I remember I mentioned that uh, that device data sets that the data sets are not always the best information that you can get. Rather, either you perform your own experiment, or you have to drop some additional, in I would say, uh, perform some additional experiment to get the right characteristic of the device at certain operating point. And this is what exactly is what we are concluding at this moment as well for GAN. So now let's move into device size and high switching frequency. Basically, this is like a discussion on what exactly could be an optimal device size that we look into GAN. So if we increase the gate width, on resistance will decrease, so the conduction loss will improve, but capacitance and the gate charge increase, so switching loss would basically worsen. The total loss curve therefore has a minimum, and this is what is being plotted in here. At low frequency, the optimum may shift towards a larger device because conduction loss dominates. At high frequency, the optimum point shift towards a smaller device because switching loss become more important. And this is what exactly you can visualize in this diagram, that there is some sort of like a balance in there. This is highly relevant when the design converters are at hundreds of kilohertz to megahertz. Many beginners choose a device with the lowest data rate R1, I would say, assuming it is the best, but that can be wrong as well. For high frequency converter, device with slightly higher R1 but much lower QG and QoS will, or I would say, may give lower total losses. So a mature designer always evaluate what type of device they are selecting, and I would say they actually evaluate the device inside the converter operating point or operating condition. For example, what voltage are you going to operate, what would be the current and the current nature of the current waveform, I would say, the frequency, cooling, dead time, and also the modulation or the switching strategy. Now let's move forward with the understanding for the high voltage devices. So technically what we are doing is that we are shifting from low voltage scaling to high voltage GAN. Now what I mean to discuss from here is that a high voltage device must support large electric field in the blocking state. In lateral GAN devices, this requires a long gate drain access region and careful field management. Current still flows laterally through the two deck when the voltage is blocked along the surface region. In vertical GAN devices, current flows through the substrate and the drift region, and the voltage is being supported in the bulk. This is more important philosophy when we have in the silicon carbide MOSFET actually. In the figure, you see in there that these two lateral and the vertical structures have been in a very top level compared, and it's defining the major resistance components, right? So the significance is very clear from this one. The lateral GAN has very strong and high frequency, are very strong for high frequency and moderate voltage, while vertical GAN is expected to be important for high voltage, high current, and possibly megawatt class system as well. However, vertical GAN needs high quality bulk GAN substrate, reliable current blocking layers, and mature processing. So there is sort of like an application promise from this like vertical GAN devices, but the technology path is still more challenging. So I would say still a lot of research are still going on in the vertical part. Now let's move towards the breakdown voltage and the drift region resistance. We had a lot of discussions about the breakdown voltage. So, what actually happens in the GAN? This is one thing that we have to understand. So, in a one-dimensional drift region, the electric field depends basically on the doping concentration and depletion width. That's what we have been learning in the silicon devices. The breakdown voltage approximately, I would say, the breakdown voltage is approximately one half of the EC. That's the equation that you see in here, right? So EC divided by mobility. Okay, I'm sorry, I messed up a bit. So the breakdown voltage is approximately one half of EC times WD for a triangular electric field profile. The drift resistance then is scales approximately with BV, which is squared by the mobility and the critical electric field, which is in the cubic form that you see in there. So that EC cube term is extremely important. It tells us why wide band gap materials are powerful for high voltage. If the EC or the critical electric field is much larger, the drift resistance can be dramatically lower for same breakdown voltage. This is one reason silicon carbide and GaN outperform silicon in high voltage power devices. But you have to also remember that this is like an ideal one-dimensional relationship that we are speaking about. Real devices has issues like field crowding, surface, traps, contacts, and packaging constraint. I think these are few points that we already discussed in the past. In lateral GaN especially, surface field management is often a sort of like a real limitation. So the equation, I would say the REP, epitaxial drift region resistance that you see in there, gives the first order physical reason why GaN can theoretically support high voltage devices with low drift resistance. We learned about the conductivity modulation in the silicon devices. If you guys remember, we were basically adding n minus and n plus regions, and also added at some moment p plus regions. So these are different types of conductivity modulation that we have been performing, right? So just a very brief revision about what exactly is those. So high voltage silicon devices often use in general conductivity modulation, and these devices could be some sort of like IGBTs which inject minority carriers into drift region. So this carriers increases the conductivity and reduces the drift region resistance. This is why we learned that IGBTs are if sent at high voltage despite limitations of use of the silicon. But the price is again the stored charge, and when the stored charge come in place, then you have a lot of limitations with the increase in the switching frequency. During turn-off, these minority carriers must be removed as well, right? So that was something that would lead to the creation of the tail current, and that's what you see in this figure, that silicon devices that rely on this type of principles. So GaN is basically attractive because its high critical field allows low resistance without relying as heavily on the minority carrier charge. This means that the faster switching and lower turn-off losses could be expected when we use the GaN. The contrast is actually fundamental. Silicon high voltage devices often trade speed for low conduction losses through conductivity modulation, and GaN aims to achieve low resistance through material properties and heterostructure design while preserving the fast majority carrier barriers. Now, I would introduce a completely new term, CAVET. What exactly is CAVET? CAVET means current aperture vertical electron transistor. It is one of the most important vertical GaN concept. In a CAVET, current flows vertically rather than laterally. The drift region supports voltage in a bulk material, and the current is guided through a control aperture. This structure is attractive because it combines the high mobility of the GaN channel with vertical voltage blocking and current spreading. The aperture region acts as a controlled path through the current blocking layer. This is conceptually similar to controlling where the current is allowed to pass in a vertical structure. The reason we discuss CAVETs is that lateral GaN devices cannot indefinitely scale to very high voltage, and current without large chip area and field management complexity. Vertical structure, on the other hand, actually offer a route to very high power density. However, the challenges would remain significant, like uh, regrowth of the interfaces, current blocking capability, leakage control, substrate cost, and etc. and etc. So now I would move forward with the most important reliability and dynamic performance issues in the GAN. Technically, what I was speaking by now was all about the benefits of GAN, A, B, C, D, E. But now let's look into what are the challenges also related to GAN. Actually, one of the most important challenges is the current collapse, right? So what exactly is this current collapse? I believe I have taught about the current collapse in the past, and also we discussed about the electric field crowding. Something similar also could be actually analogously discussed in the GAN as well. So what actually happens in the current collapse? I would say that the surface trap and the high field crowding that you see in here can trap the charge during high voltage operation. When the device turns on again, the trapped charge partially depletes the channel, so the dynamic on resistance become higher than the static value measured in the dataset. This is basically the current collapse or the increase in the dynamic on resistance. Field plates can be used to basically this field plate could be actually be used to in a way reshape the electric field, right? So they split the electric field and reduce the peak field near the gate or drain, and once we have it, then we are able to suppress the trapping effect and improve the breakdown voltage. This is what you see also in this diagram. The main point is that GAN cannot be judged only from in a value of a static resistance R on, but we have to always consider that there is a dynamic RDS on or R on. That means that the conduction loss will actually vary based on the operating point of the system. So a device may actually look excellent in DC measurement, but may suffer from any other dynamic operating point under, for example, hard switching or any other soft switching. So for real converters, we must evaluate the device under different voltage, stress, switching frequency, temperature, and layout condition. So how exactly we would basically evaluate this vertical GAN devices is the first thing. We know that the vertical GAN devices has basically evolved through multiple generations. So there have been multiple things that has been done around it, and but the progress in general remain focused on few major parts. That's the increasing the breakdown voltage, reducing the leakage, lowering the turn or on resistance, and achieving normally off operation. Vertically GAN devices that are in the research are also now basically approaching kilovolt class operation with milliohm range resistance, which is really something that has not been established in the past at all. Now let's try to understand what exactly are the requirements for a practical power GAN devices. In the first lecture, I was speaking about different systems, and from the requirement of the system, how exactly you will move towards selecting a particular device, or maybe selecting a different component, or selecting a different topology, right? So something similar could also be analogously visualized in this case. First, normally off operation is essential for power operation, right? This is what we already know. Second, we need high breakdown voltage beyond low voltage adapters and I would say point of load converters. Third, low on resistance is necessary for high efficiency. Fourth is the high current density, which is needed to reduce the chip size and obviously at the end cost. Fifth is high temperature operation is required for compact system to make sure that the cooling system doesn't become too bulky. So this is what exactly the slide lists about the practical route of normally off operation. So this could be achieved by different types of structures. So one is P-GAN, then we have resist GAN, then we have fluorine implanted, then cascode silicon GAN. There are actually many other type of GAN devices also in the market, but we will remain focused with this few type of devices only. So each of them has some sort of compromise. What are those compromise? For example, PGAN is commercially important but has gate drive limits. Resistance gate could be elegant, but it depends on the process control. Again, fluorine treatment affects threshold but raises stability questions. Cascode is easy to drive, but it adds series resistance and parasitic. So each of them has got some sort of benefit and challenges, I would say. Now let's move forward uh, towards one of these of the different types of devices, I would say. So we start with first depletion mode, GAN hemmed structure. What exactly is the depletion mode? D mode is technically normally off type devices. Here we will learn about the transistor structure, I would say. So the basic GAN hemmed has source, gate and drain electrodes, which is placed over a ALGAN or GAN heterostructure. The source and drain connect via or connect to the 2-deck, which acts like a lateral conduction channel. In a depletion mode hemmed, this 2-deck exists as a zero bias, so we don't have to apply any bias, and still it will exist because it's a normally off. Therefore, therefore to basically turn it off, we apply a negative gate voltage that depletes the 2-deck under the gate. This figure clearly shows that the negative gate bias basically repels, it's basically repelling the electrons and interrupts the conduction path. This structure is physically simple and can be excellent performance, but not ideal for power converter safety. If the gate driver fails to or loses supply, the device may uh, turn on by default, and this is something that we really don't want to have in case of power converters. The other type of structure is basically Schottky gate and the or maybe insulated gate D mode hemmed. Both are being shown in this slide to you. The Schottky gate hemmed uses metal gate directly to the ALGAN barrier. The gate controls the 2-deck electrostatically by changing the field of the barrier, and this structure is, I would say, relatively fast and simple as well. But gate leakage can be an issue because the gate is a metal semiconductor or MOS junction basically, or let's keep it simple, metal semiconductor junction. The insulated gate hemmed, on the other hand, places a dielectric between the metal gate and the semiconductor, and this reduces basically the gate leakage and makes the device more like a MOS-like structure. However, when we introduce a dielectric, interface quality becomes critical, which means that traps, fixed charge, dielectric breakdown, and threshold stability becomes major concern. This is what is being shown in this figure as well, that there is how exactly they are structurally different. I need to emphasize that the gate technology in the GAN is not just about applying voltage. It actually determines the leakage, reliability, threshold stability, and also most importantly the switching behavior. So basically I would say that the same ALGAN channel can behave differently depending on how exactly the gate is being stacked. Right, so there you will see a lot of modifications in the gate that is being performed over time to in the gate actually. I think this was also something that we observed in the case of silicon carbide MOSFET and silicon devices as well. So you guys could just have a look into the previous device structure also to get the same idea. Now, why normally off GAN is basically required. In power converter, the safest state is off. During startup, shutdown, controller reset, or I would say gate driver fault or auxiliary power supply failure, the switch must conduct unintentionally. A normally on GAN device basically violates this expectation unless there is additional circuitry that is being used to determine if there was a fault or something around it. On the other hand, an enhancement mode or E mode device or normally off device at a zero gate bias is basically off at zero gate bias and turns on only when a positive gate voltage is being applied. This is what is being shown in this figure actually. It is seen here. So at zero bias, the channel under the gate is depleted while With positive bias, the electrons are attacked back, I would say, and conduction is being established. This is the same safety philosophy we actually had in the silicon MOSFET also. I would say more technically enhancement mode silicon MOSFET, right? So in the E mode silicon MOSFET that I'm speaking. However, the difference in the GAN is that the physics is different because we are not working with the charging and discharging or inversion or accumulation layer. Rather, we are working with the underlying principle of 2-deck, which naturally want to exist. So E-mode GAN is not just a gate driver choice, it's a device engineering solution to force normally off behavior while preserving the low resistance. Now let's learn about another one, that's the resist gate E-mode GAN. The idea is to etch away part of the Algen barrier under the gate that you see in here. So a part of it has been etched away since the 2-deck density depends strongly on the Algen barrier thickness and the polarization charge. Thinning the barrier reduces the electron density under the gate. If the barrier is then thin enough, the 2-deck is depleted at 0 gate voltage. When the positive gate voltage is applied, the electrons are attracted back to the interface and the channel is basically restored. The figure that you see in here basically illustrates that this local barrier is thinning. The advantage is that the normally off behavior can be achieved in a compact single chip device. The challenge is still the precision, right? So manufacturing challenge comes in there. So if the resist is too shallow, the device may remain normally on. If it is too deep, you may damage it basically, or mobility would decrease, or the leakage would increase, and the reliability of the system itself may be under challenge. So therefore, resist GAN is a good example of a structure where I would say nanometer scale fabrication control directly, but it determines the behavior of the device itself. The other type is the fluorine implanted enhancement mode GAN. Right, this guy is actually very nice one, majorly not commercialized, I would say, to the best of my knowledge. Rather, it's more in the research perspective. So what actually happens is that the fluorine atoms is being implanted, that you see in here, right? So this is being implanted in here. So these atoms introduce a negative fixed charge in the Algen barrier, right? So there is a negative fixed charge in here, and this negative charge repels the electrons and locally deplete the 2-deck under the gate. With this 2-deck depleted at 0 bias, the device becomes E mode. When the positive gate voltage is applied, the electric field from the gate can reconstruct the channel, and this is what the figure also shows the same idea. So conceptually, I would say fluorine implantation is basically attractive because it shifts the threshold voltage without necessarily removing the barrier by etching that we were doing in the resist GAN. However, the reliability is another question, right? So reliability again is a question. So fixed charge may not remain perfectly stable under high field, high temperature, and repeated switching. Trapping and detrapping can lead to threshold voltage drift. Therefore, when we discuss this approach, we must distinguish between, I would say, achieving a positive threshold voltage in a fabricated device and maintaining that threshold over years. But we also must remember, I would say, that the device reliability is sort of like a time dependent solution. Okay, so it's not like the reliability of device remains same throughout its life, but it actually changes over time. Now I bring to you the P-GAN gate E-mode structure. P-GAN gate is one of the, I would say, most commercially commercially used structure right now in the market. So how exactly it works and what exactly is there in there. So in a P-type GAN, I would say that this is what you see in here. There is a P-type GAN layer being grown on the top of the Algen barrier. The built-in potential associated with the P-GAN stack depletes the 2-deck under gate at 0 bias. When the gate is driven positively, the channel is restored and the current flows. This is what exactly you see in this diagram as well. The P-GAN approach has become very popular because I would say it is practically a normally off device with a really good performance, but it introduces an important GAN drive constraint. The gate is not an ideal MOS capacitor like a silicon MOSFET. Gate current and gate voltage limits must be respected. Overdriving the gate can actually damage or degrade the p-GAN gate stack. Threshold stability is also important, therefore p-GAN require careful gate drivers, typically with tightly controlled positive gate voltage, low inductance, and protection under the overshoot. Now, finally, we have got the final device, I would say, that's the hybrid normally off devices. What exactly is the philosophy of a hybrid? You could imagine that there would be some sort of like mix of two different technology or methods that will be performed. So, what exactly is being done in the GAN? So, instead of making GAN transistor itself E mode, what we could do is that we can combine a normally on depletion mode or normally off GAN hemmed with a low voltage silicon MOSFET, right? So this is something that we already discussed in previous lectures as well, if you guys remember. So that is the cascode configuration that we are speaking about. So in the cascode configuration, the silicon MOSFET controls the source potential of the GAN hemmed. When the silicon MOSFET is off, the source of the GAN devices moves such that the GAN gate source voltage becomes negative, turning the GAN hemmed off. When the silicon MOSFET is on, the current flows through both devices. This is what you can see in this diagram as well. Right? The advantage is the compatibility with the standard MOSFET gate drivers and normally off external behavior. The disadvantage is added series resistance and packaging complexity, parasitic interaction between these two devices, or a lot of things that comes and goes around. So cascode GAN is therefore attractive for simplicity and robustness in some application, while single chip enhancement mode GAN may be preferred where the lowest capacitance and faster switching are required. Now let's move towards the cascode GAN with understanding a bit of a cascode GAN as well. I would say I'm focusing a bit on the cascode GAN at the moment because cascode GAN was one of the first commercially available GAN devices in the market, and they were actually in use for quite some time, and they are still in use. People still prefer those, although p-GAN gate structures have been taking over the market slowly, but I would say they are still in use. So a bit of more discussion on this topic. So the key question in the cascode GAN is that how much resistance does the low voltage silicon add, right? This is something that we must understand. So at high voltage rating, the resistance of the high voltage GAN hem dominates. So the contribution of the low voltage MOSFET would be relatively small. This is why cascode structure are actually very attractive at 600 volt and above. But at lower voltage rating, however, the GAN device itself may have a very low resistance. So the silicon MOSFET resistance contribution becomes more significant. This is what you see in this diagram as well. So there is a sort of like a percentage trend that you see in there. So the design lesson is that we must evaluate the complete series conduction path, not just only the GAN component, when we try to select a cascode GAN device. In cascode device may look like a single 3-terminal transistor from outside, but internally it's a composite switch. So its losses, capacitance, switching speed, reverse conduction behavior, these are all influenced by both devices and their interconnection and the interplay between them, rather than assuming that it is being just one device. Now let's move forward and try to understand the electrical characteristics a bit about it, right? So I will start with the reverse conduction in the E mode or enhancement mode GAN device. That's the normally off GAN devices. E-mode GAN hems can conduct in both directions through this channel. During reverse conduction, device does not use conventional body diode because lateral GAN hems do not have the same PN body structure as silicon MOSFET. Instead, when the drain potential becomes sufficiently lower, then the source and the gate conditions allow it. The 2-deck channel is restored and the current flows in the reverse direction. This is what you see in the diagram as well. There is not much change in what exactly is happening, but still it is able to perform forward current flow and the reverse current flow. This gives like a diode-like functionality, but without minority carrier reverse recovery. This is one of the major advantages in the high frequency half bridges. However, reverse conduction voltage can be higher if the gate is off. Therefore, the dead time optimization and the synchronous gate control are very critical in case of this type of devices. A common mistake that is that we assume that GAN reverse conduction behave exactly like a MOSFET body diode, but you have to remember that it does not. It is the channel based and the gate condition dependent. Now let's move further with a bit more discussion about the difference from the silicon MOSFET. As I already mentioned, that reverse conduction in the GAN should not be assumed as a body diode that is being body diode in the silicon MOSFET, right? So in a silicon MOSFET during that time, in a half bridge, the reverse current often flows through the intrinsic body diode, the diode that is formed by the PN junction and therefore involves minority carrier stage or a storage. When the opposite switch is turned on, the stored charge must be removed, creating a reverse recovery current and I would say extra switching losses. But in E-mode GAN, reverse conduction is mainly channel based, the two-deck channel that we are speaking about. There is no body diode present in there. Therefore, the conventional reverse recovery charge is essentially basically absent. This is one region GAN performs well in high frequency, high switching application, but there is always a trade-off, right? So if the gate is not driven properly during reverse conduction, the source to drain voltage drop can be relatively high, increasing dead time loss. The key message I would say is that we must have is that GAN reverse recovery conduction reverse conduction is controlled by the channel deformation and the gate bias condition. A good GAN gate driving is not only about turn on and turn off, it is also about managing the reverse conduction interval. That's the dead time part, and the gate drive voltage and everything around it need to be managed very well. Now let's compare different types of E-mode GAN approaches, and that's how we would basically conclude about different types of GAN devices. So the resist gate that we discussed directly depletes the two-deck under the gate, but it is sensitive to each damage and interface quality. When we look into the fluorine implantation, then it uses a negative fixed charge, right? That's what the fluorine implantation will do that, but the threshold stability can again be challenging. P-GAN gate technology is commercially important and has been widely used, but again it requires careful gate voltage limitation and understanding of the gate current. Cascode and the hybrid GAN uses low voltage silicon MOSFET with depletion mode GAN. It is compatible with the standard gate drivers, but again it adds series resistance and package complexity. So direct drive hybrid structure can offer more control of the GAN HEMT, but the gate drive supply becomes more complex. I need to emphasize that there is no universally superior normally off solution in the GAN. The best choice of yours would completely depend on what voltage class are you working on, what is the switching frequency, what is the level requirement, what is the cost that you are looking into, what is the driver complexity, and also the application environment in there, right? So I would say for every application you could say that I will be able to I should be able to use X or Y, anything that you would like to take away. So now we finally conclude the design for the GAN transistor structure. The natural AL-GAN or GAN 2-deck makes GAN HEMT very conductive or highly conductive, but it also makes it normally on, right? So power electronics in general would require normally off behavior for safe startup, shutdown, and fault response. And that's where E-mode comes in place, and this could be achieved through resist gate, implanted charge, P-GAN gate, and hybrid cascade structure. Each methods have certain trade-offs and things around it. So I would say that the main central message from my side would be that the GAN transistor design is about controlling two-deck. We form it for low loss, deplete it for normally off behavior, and restore it during control conduction. If you understand this cycle very well, form, deplete, restore, you will basically be able to understand the physical heart, or you can understand the physical heart of the GAN power transistors. Now we are moving towards the characteristic. I would say this is something that we have been doing for all our different devices also that we learned. Technically I should have taken a break by now for continuing this part, but since this is a recorded lecture that I will be sharing with everyone, I would say that I will keep going. You could always pause the lecture at this moment and then take a break and then come back again, right? So this is the part that would be very important when we are looking into the converter design aspect. So a GAN transistor must be judged by, I would say, drain source breakdown voltage, leakage current, on resistance, threshold voltage, capacitance, gate charge, and reverse conduction. These parameters would determine whether the device can survive the voltage, carry the current, switch at a required speed, remain thermally safe, and avoid unwanted turn-on. It is tempting to compare GAN devices only by RDS on because conduction loss is easy to understand, but as I mentioned, this is totally incomplete, right? So a load resistance device with high capacitance may actually perform very poorly at high frequency. A device with low threshold voltage may be very difficult for us to design a work with a gate drive circuit, and a device with excellent static leakage may still show dynamic our own problem. Therefore, GAN devices must be evaluated both statically and dynamically. And this is what exactly we are going to learn in the next few slides. Let's start with the drain source voltage reading. What exactly it tells us? It defines as the maximum voltage device can block when it is off. In the off state, the gate must prevent the formation of the conduction path between the drain and the source. Breakdown can obviously occur if the electric field must basically exceed the limit of any critical material region, GAN, ALGAN, gate dielectric, passivation layer, surface isolation or surface insulation or anything around it. But this is very important that the breakdown voltage of the finished device is not simply the ideal critical field of the bulk GAN material by distance. Practical breakdown is often limited by field crowding, surface traps, dielectric failure, and layout, design of the device, and a lot of things around it. This is what exactly is being shown as an example of what exactly a reverse bias condition for E mode and D mode transistor would look like. The figure helps us to see whether basically the voltage is applied. The figure helps us actually to see where the voltage is applied and where the gate is used to keep the channel depleted. In a real actual power converter, transient overshoot from the parasitic inductance can actually lead to nominal DC bus voltage. So voltage rating must include switching margin, not only the steady state voltage that is being defined. I think this is a completely new diagram that I am showing here. In the past, how we have been learning about the electric field distribution was basically by drawing electric field diagrams, right? But this is a different one because there is not much discussions of the electric field in the way that I have discussed in the past. So I would just follow a particular textbook. And this slide or this diagram basically shows why electric field distribution matters. If you look into this one, then during blocking, the high electric field often appears near the drain side edge of the gate. If the electric field counter line are close together, the local field is high. Breakdown begins at the weakest local point, but not necessarily when the average field reaches the theoretical material limit. Therefore, a device designer use examples like use sort of like field plate or optimize gate drain spacing, surface passivation, or anything around to make sure that the electric field is distributed more uniformly. The figure that you see in here is sort of like a warning against one-dimensional thinking. Ideal equations are useful, but real devices actually fail at local field, which could be a sort of like a peak. So if a converter designer, or I would say for a converter designer, this also connects to the dynamic voltage stress. A fast turn-off can generate voltage overshoot and ringing. Even if the steady state DC voltage is within the rating, repeated transient peaks can stress the passivation or gate drain region. So a good GAN design therefore combines the device level field management and circuit level over voltage control. Now let's try to understand the leakage current component. I would say this is also very critical and very important because when the GAN transistor is off, the leakage current still exists, right? So the lower, the best. The total drain source leakage can be composed of drain to source leakage through the semiconductor, drain to gate leakage or around the gate structure, and the drain to substrate leakage depending on the device and the substrate configuration. The figure that you see in here shows that separates this current path, right? So there are three different things that that are listed out here, and each of them are being separated. And then we also have a total drain source in there. In high power converter, leakage may not dominate at full load, but it can matter at a standby operation as well. High voltage blocking intervals, thermal runaway analysis, and etc. etc. So leakage is basically also a diagnostic indicator. Excessive leakage can lead to field crowding, surface degradation, dielectric stress, or it could be a manufacturing defect as well, right? So we should be able, if we have a higher leakage, then we could say that okay, this device is not a particle one that we really want to have. So when reading a data sheet, I would say you should always check the leakage test condition, for example, the VDS, VGS, temperature, and measurement criteria. A leakage current is, I would say, in general, in a data sheet is specified at 25 degrees Celsius, which is much lower than the leakage at, I would say, a higher temperature of, for example, 125 or 150 degrees Celsius. So I must emphasize that the voltage rating is a sort of like a field distribution problem, and the ideal material may have very high critical field, but real devices may fail at local field peaks, gate edge, and other things around it. So I would say it's very important that you should also try to identify where the electric field is the highest in a particular device, and this would actually help you to understand this leakage part very well. Now, as I already mentioned, that data sheet gives you only about 25 degrees Celsius leakage current at 25 degrees Celsius, but in actual, it's a very different story, and this is where exactly you come to see around what exactly is the temperature dependence of the leakage. As the temperature increases, the carriage generation increases, and the trapped charge related conduction path may also become more active. This is what is being shown in this figure, that both temperature dependence and the device to device variation. The variation matters in production system because a design must tolerate the worst case device, not only a particular typical curve. So leakage also affects thermal design, I would say, through feedback. Higher temperature increases leakage increases power dissipation would increase the power dissipation will further increase temperature. So it's a sort of like a vicious cycle that goes on till the device completely fails or they burn. So in GaN, this feedback is unusually very less severe than in narrow band gap material, but it is still relevant near maximum voltage and temperature. Data sheet is specifically leakage at particle VDS, VGS, and junction temperature. If two manufacturers use two different conditions, or I would say different test condition, then this leakage can also be comparatively different. So I would say that as a matured engineer, what you should do is that you should try to normalize condition or test device under actual converter stress profile before selecting the specific device. Now let's try to understand the device ratings. First is the BVDS and IDSS. What exactly is the BVDSS? So that's the breakdown voltage that we are speaking, and the ID is the drain current, right? So okay, so yeah, this values are basically different in datasheet section. So absolute maximum rating, static electrical characteristic that you see in here, then and sometimes transient rating as well. This is what is being shown in this figure as well. So the main point is that datasheet values are not universal constant. One device may specify a breakdown at a current of a few microamps, another at a different current. One may specify leakage at 25 degrees Celsius, other can also at higher temperature. Therefore, when comparing GaN devices, do not simply copy one number into a table, compare test condition, also check transient capability. Some GaN devices can tolerate short overvoltage pulse above nominal rating, but it depends again in the duration. So duration can also vary, repetition, how much times you are repeating, then maybe temperature and manufacturer qualification also. There are a lot of things that is, I would say, that need to be taken care of. Uh, to my understanding, data sheet interpretation is not engineering, I would say, rather it's more about a sort of like a bookkeeping work. Bookkeeping means that you actually have a connection between X to Y, Y to Z, and likewise, right? So you have a total sort of like a complete connection between one point to another, and that's how you exactly interpret a data set, interpret the data set correctly. On resistance components in the GAN HEMS. So what exactly I want to discuss in this one, and this is very important, I would say, because GAN HEMT is not one physical register, as we discussed that it's actually having a dynamic resistance, right? So what exactly does that mean? In the diagram, you can see that it is the sum of the contact resistance, access region are 2-deck resistance, and gate region resistance, and metal routing resistance, and the package resistance. So equation that you see in here summarizes the HEMT contribution at the two contact resistance pulse plus 2-deck resistance outside and under the gate. What exactly it means is that the two is something that each of this different, I would say, parts has certain contribution, and the properties of each of this part would actually dominate the overall value of the resistance. And this is where exactly the critical part of how exactly it's a dynamic resistance comes in place. The 2-deck resistance depends on mobility, sheet carrier density, and the channel width. Contact resistance depends on ohmic contact quality, metallization, and the process technology. Package resistance and the PCB interconnection becomes important because GAN devices can also have very low die resistance. So in high voltage, high current, low voltage, high current application, a few milliohm from package or layout can be significant, right? Therefore, when the data set gives you a value of RDS on, remember that it is terminal measurement. It's a terminal measurement. I'm repeating again. It includes mainly physical contribution. For design and failure analysis, we often need to know which component dominates and how it changes with voltage, gate bias, and temperature. Again, we need to now look into the temperature dependence as well, right? So RDS on increases with junction temperature that you can see from this plot itself. In GAN HEMT, a major reason is the reduction in the 2-deck mobility with temperature. As the lattice vibration increases, carrier scattering increases and mobility would decrease. Contact and metal resistance also vary with temperature, but the 2-deck contribution can dominate. This is what you see in the equation here. The conduction loss equals RMS current squared time RDS on at the operating junction temperature. This is why the 25 degrees Celsius data sheet value for a loss calculation can be really dangerously, I would say, optimistic. Also, I would say remember the feedback loop, right? So higher RDS on increases losses, higher losses again increases the temperature, and higher temperature further increases RDS on. So a stable thermal margin design must close this loop with sufficient cooling margin as well. The cooling is something that we plan to learn in the next semester, but I would say that there is some basis that is being formed at the moment as well. I have also been speaking for quite some time that for low voltage the RDS may be lower, for high voltage or I would say so there is some dependency in the gate voltage as well with the value of RDS on, and this slide actually shows that the GAN on resistance depends strongly on the gate source voltage. So at low gate voltage, the channel under the gate is not fully enhanced, so the resistance is high. As the VGS would increase, the 2-deck channel is restored more fully and the RDS on basically decreases. That's what you see in here. Beyond a certain gate voltage, additional increase gives only limited improvement because the channel is already strongly enhanced and other resistances would typically dominate. The practical lesson I would say is that the GAN must be driven with recommended gate voltage. Underdriving the gate may reduce gate stress, but obviously it will increase the conduction losses and junction temperature, and overdriving may actually damage the gate structure itself. So GAN driving is, I would say, a very narrow window design problem, high enough for low resistance, low enough for long-term reliability, and stable enough for avoiding ringing beyond limits. Right. So if you guys remember, then threshold voltage, I would say the driving voltage in case of MOSFET was quite wide. It was somewhere in the range of 12 volt to 21 volts, depending on the type of manufacturer, so silicon to silicon carbide. But in case of GaN, it's very small. In general, for a E mode, it's somewhere ranging in terms of 5 to, 3.3 to 5 to 8 volts. So maximum, this is what we apply in there. Now let's try to understand the datasheet specification. So datasheet specify RDS on under certain defined condition. That's what is we already have learned. So that would be certain gate voltage, drain current, and temperature. At low voltage, GaN devices may specify RDS on at 5 volt gate drive, while the higher voltage could be that they define at 6 volt. This makes the direct comparison non-trivial, right? Typical values are useful for estimating average performance, but maximum values are more important for thermal design and guaranteed operation. You see a datasheet example in here, right? So you can see the difference that what I'm speaking about. So when designing a converter, I would say that use the maximum hot RDS on wherever possible. Also check whether measurement is pulsed, because pulse testing avoids self-heating and may produce lower resistance than continuous operation. In GaN devices, dynamic RDS on can also be higher after high voltage stress due to trapping. Therefore, a complete design should consider static RDS on, temperature dependence, and dynamic RDS on behavior under switching condition. Okay, I went a bit fast with in those one. So now coming to the threshold voltage in GaN transistor. I think the importance of threshold voltage has already been defined multiple times in the lectures. I would avoid speaking a lot about the relevance of threshold voltage, but let's try to understand the threshold voltage in GaN transistors and how they vary with the change in temperature. This slide actually shows you directly, the plot actually shows you directly what I want to say. So in generally E mode GaN, you have got a positive threshold voltage. So depletion mode GaN has negative threshold voltage. In GaN, threshold actually depends on the polarization charge, Algen barrier design, gate stack, p-GaN layer if present, and temperature. It is important to distinguish that the threshold voltage from the recommended gate drive voltage. A device may begin to conduct at around 1 to 2 volt, but it may need 6 to or 5 to 6 volt for low on resistance. Threshold voltage is mainly a noise margin, I would say, and a false turn-on parameter, because you know that 1 to 2 volt is not a big number to achieve while we drive a device in a system. So a low threshold helps low voltage drive, but also increases sensitivity to the gate ring and Miller coupling. Therefore, threshold voltage must be interpreted together with the gate resistance, layout inductance, driver impedance, and dV by dt. Now let's try to understand it as a differentiating between the silicon and the silicon MOSFET and normal GaN. So as already known, the GaN transistor has the threshold voltage often lower than the silicon power MOSFET. This gives fast and low voltage gate control, but it reduces the noise margin. Compared to silicon MOSFET, GaN threshold voltage can have a smaller temperature variation, as you see in this slide actually in the plot. However, the absolute threshold margin is still small. A few hundred millivolt of gate ringing may matter actually. False turn on must be avoided in half phase operation, especially when the opposite devices switch at high dV by dt. Negative gate undershoot must also be controlled, because excessive negative voltage can stress the gate. For GaN, the real concern is actually the combination of low threshold, high switching speed, and strong capacitive coupling. This is why GAN layout must use strong gate loops, Kelvin source connection when available, and carefully selected gate resistance. Now we are moving towards the datasheet specification of the threshold voltage. So a datasheet threshold is measured at a very small range current criteria. It tells us when the device begins to conduct. It does not tell us the gate voltage required for efficient power conduction. This distinction is essential. A GAN transistor may have a threshold near 1.5 but require 5 to 6 volts for full enhancement. Right, this is what exactly is being mentioned in this datasheet snapshot also in there. The threshold voltage is useful for accessing noise margin, fast turn-on risk, and the gate diode protection. It is not a conduction loss design value. Also, notice that I would say that the spread between the minimum, typical, and maximum threshold voltage in production, because of the production or the manufacturing, also these things could vary. So a driver and a protection circuit must work for minimum threshold device, which is most vulnerable to fast turn on, and for the maximum threshold device, maximum threshold device, which may have a higher resistance at a given gate voltage. So a gate drive design always accounts for this distribution. Now we are coming to almost towards the end, I would say, by starting discussion on the capacitance in the gate in the GAN register. If you look into this diagram, I would say this is not something new that you are learning, right? So this is something that we have been discussing for quite some time. So we all know that the switching behavior in the devices are in the power semiconductor devices are usually dominated by this type of capacitances. So similar is the case of GAN. So that means that in GAN also it is dominated by this terminal capacitances. There are three intrinsic capacitances, so gate to source capacitance, gate to drain capacitance, and drain to source capacitance. Datasheets usually report combinations, as I already discussed about CISS, COSS, right? So this is what is being done, and CRSS. And you can see in this diagram that how exactly these capacitances are being placed. Okay, so apart from that, CGD is especially important because it provides the feedback from the drain to source voltage, drain to gate voltage, and it's also the CGD is basically the Miller capacitance. CDS and CGD together determine the output capacitance, which affect the soft switching energy, voltage transition time, and ringing. So in GAN, capacitances are often small, which enables fast switching, but their small value also means that parasitic capacitance and layout capacitance become comparatively important. A few picofarad of unintended coupling can influence switching behavior. Therefore, capacitance is not just a data sheet number, but also, I would say, very important for entire converter electromagnetic design, especially when we go into the soft switching power converters. I would say this become more and more increasingly relevant. Now let's try to understand the voltage dependence on the GAN capacitances. So GAN capacitances are actually very strongly dependent on the voltage. As the VDS will increase, the depletion region expands and the effective capacitance often decreases. COSS is especially important because it stores the energy that must be transferred or dissipated during switching. This is what you see in this diagram, that the capacitive variation, how exactly this capacitance would be varying with the drain to source voltage. At low voltage, capacitance can be relatively high. As the voltage increases, it drops. This non-linearity matters in resonant converters, soft switching transitions, and hard switching energy calculations. If we use a single capacitance value, we may miscalculate the transition times and energy. For accurate loss modeling, we often use output charge QSS or a stored energy USS rather than constant capacitance. In GAN converters switching at very high speed, COSS also interacts with loop inductance to produce ringing. Therefore, I would say that it's very important to understand the voltage dependency of the capacitance for both having better efficiency and also for better EMI and other things around it. Now, gate charge and the Miller plateau, right? So we always know that we don't want a very big time interval for the Miller plateau. We always want to get rid of the Miller plateau. So let's try to understand this part as well in this case. So gate charge tells us how much charge the gate driver must deliver to the device when it's turned on. It is basically the integral of the gate current over time. That's what you see in this equation, right? So Q is equal to integration of IGT. The gate charge curve links charge to the gate source voltage. The near flat portion is the Miller interval, where much of the gate current is used to change drain source voltage rather than raise gate voltage. This is a device that you see in from the EPC. Lower gate charge is one of the main reason GAN can switch quickly and with low gate drive losses. But fast switching is not always better. If the voltage changes too quickly, dV by dt increases EMI, includes a common mode current and can cause fast turn on in the complementary switches. Therefore, a gate charge must be interpreted together with the gate drive current, gate resistance, layout inductance, EMI limits, and I would say a few more things if the gate drive circuit is really very complex. So in practice, we often intentionally slow down a GAN device to achieve a reliable power converter. This is example of a dynamic datasheet parameter that you have got in here. So dynamic datasheet parameters are technically essential for gate driving and switching loss design. So CISS, CUSS, CRSS describe capacitive behavior. QGS, QGD describe the charge required for different parts of the gate transition. QSS describe the output charge. Internal gate resistance influences how fast the gate voltage can change with the ideal external driver. These are all things that you see in there, and there is also an equation that gives a simplistic estimate of minimum gate voltage transition time using a gate charge, gate resistance, and a gate voltage. The data sheet that you see in there shows the dynamic properties. So this is simple estimate, I would say, but it's also very useful. But you have to remember that real switching also involves driver resistance, external gate resistance, package inductance, source inductance, load current, DC bus voltage, and nonlinear capacitance. For GAN, dynamic parameters are often more important than static parameters because converter benefit comes primarily from fast switching. A device cannot be simply selected properly without understanding of this QGD, QSS, and CRSS, I would say. Now we learn about the reverse conduction. I already mentioned that compared to the conventional silicon MOSFET, there is no body diode, but they still conduct in the reverse because of the presence of the two-deck channel. So if the gate is driven high enough, the reverse conduction can occur with nearly the same on resistance as the forward conduction. If the gate is off, large source to drain voltage is required to re-establish this conduction. This figure shows basically the source to drain current versus the voltage behavior. This is extremely important in half-bridge converters, where I would say during dead time current must continue flowing through one of the devices. If the dead time is too long and the gate is off, the reverse drop can actually be high and the loss would increase. So if a synchronous gate control is well timed, reverse conduction losses can be minimized. Therefore, I would say the dead time optimization in the GAN is super optimal. Like, it's very important. It is the central way to achieve high efficiency and actually avoiding unnecessary heating in the system. So now I would say we just have a small comparison of how exactly it is compared, reverse conduction is compared with the silicon body diode. I believe the understanding of the process is already clear, right? So in silicon MOSFET, the reverse conduction typically flows through the intrinsic body diode during that time. This diode stores minority charge, and when the current commutes, the reverse recovery occurs. Reverse recovery create current spikes, additional losses, EMI, and device stress. In the E mode or normally off GAN, there is no minority carrier that would cause the reverse recovery at the same sense. So reverse recovery charge can effectively be zero. This is one of the major advantages of that is very much useful for high switching frequency power converters. The trade-off is, however, that the reverse voltage drop under off voltage condition. If the gate is not driven properly, the GAN reverse conduction can dissipate significant energy. This is what you see in this diagram as well, that it compares the reverse conduction data. in practical, I would say the practical message that you should take from this slide is that the GAN eliminates the reverse recovery problem but introduces a gate timing problem. We reduce losses not by relying on diode but by actively controlling the channel during reverse current interval, right? So this is all about the reverse conduction, and finally I would say this is the final slide of what exactly would be the design takeaway from the GAN electrical characteristic. So BVDS and IDSS define the voltage blocking and the leakage behavior. RDS on determines the conduction losses, but it increases with the temperature and can be affected dynamically by trapping. Threshold voltage is low, so noise immunity and the false turn-on prevention is critical. Capacitance and gate charge determine switching speed, switching losses, and EMI sensitivity. Reverse conduction is the channel-based and avoids conventional reverse recovery, but it must be managed through proper dead time and gate control. So I would say that the central lesson is that the GAN cannot be just from RDS on alone or the voltage breakdown voltage alone. A good GAN converter requires simultaneous optimization of device selection, gate driver, PCB layout, dead time, thermal path, and EMI control. If you remember one thing from this lecture, remember this, that the GAN gives enormous performance potential, but it gives that potential only the designer who respected speed, low threshold margin, non-linear capacitance, and 2-deck conduction physics. Okay, so it's not like you just use a device and make it exploit it. You must also respect its limits and what is actually running in and around that to make sure you get the most optimal performance of the device. Okay, so this is all for today. I would say that in some places I actually went quite fast, I would say, but since you guys have got the way to slow down the lecture as well, I would say if you have any trouble, please slow down the lecture at the moment, and if you are not able to understand certain point, you are actually welcome to reach out to me, and I would be very happy to discuss about the device that we learned today, that's the GAN. From the next lecture, we would be targeting to start the passive component, I would say, unless I come up with a new idea about what more could be taught in terms of device, power semiconductor devices, but I believe we will be starting to learn about passive components from the next lecture. My colleague Andreas would be taking full day tutorial on 17th, and post that we will start learning about capacitor, inductors, and few other things. That's all for today. Thank you everyone. I hope people actually view this lecture till the end and come to me with certain questions if they have got in there.